All right, this is part two. Same stuff with the advanced hybridization overlap. I just wasn't able to get all the information in that one video, so I want to continue on a little bit here. Okay, so I did SP3, and I showed you here the SP2 hybridization. Now, everything I'm showing you, even though I'm using carbon atoms, it's the same with any atom. The only difference is there might be more electrons. Like, for example, like there's a problem on your paper. It talked about phosphorus. Let's see. Like, number one, do carbon unhybridized. I did that for you. SP2, I did that. You don't have, when I say do SP2, you don't have to draw two of them. You can just draw one only. But I'm just showing you by putting two together how to make a double bond. How to make a single bond. Nitrogen unhybridized, then with SP hybridization, nitrogen. Then the phosphorus with sp3d hybridization. Okay. So I think I'll show you a lot of these. Like I said, I'm not going to make you draw them really, but if you're able to, it helps a lot. So let me do, but what I was going to tell you, like say if you did a nitrogen atom, like here's a carbon atom, and I showed you the carbon was sp3 and sp2. Just say if it were a nitrogen atom, all right, well then the only difference is, of course, nitrogen has an extra electron. After carbon on the chart, you see that it has, it's 2s, 2s2, 2p3. So then I would put one more. Well, actually, I have an electron there left over. So nitrogen would actually be that. Carbon, it just has 2s2, 2p2. Nitrogen, 2s2, 2p3. And you draw the same exact diagram, but you just put one more electron, as I showed you, if you're doing sp3 or sp2 hybridization. Anyway, I'll do one here. Let's do sp hybridization. Now, I can do this for carbon or nitrogen. It doesn't really matter. I ask you to draw an unhybridized. I'll tell you, you can, if you want to, the top part, I'm kind of doing this for you, but you don't have to do this top part, okay? But as I'm doing it now, you might want to. You might want to try, but it'll be the same. I'll do a carbon, unhybridized carbon atom again for sp hybridization. I'd rather stick with carbon because that's going to be something that might relate to the organic questions. Remember I told you the organic chem comes into this chapter. So, well, I should say what AP asks about organic is associated with this stuff we're doing now in this chapter. So, sp hybridization. So carbon starts off, spp, and other atoms, will have the 5ds. But if I have sp hybridization, that means only two orbitals combine. And so you end up getting an s with one p, and you get two sp orbitals, and then you're going to have left over two p orbitals left over. So it's good to know what orbitals you used. Well, before you had one s, an s orbital, and you had three p orbitals. Okay, an s p p p. Before, technically it was a 2s and the 2px, 2py, 2pz. Okay, afterward you're going to have two hybrid sp orbitals, and you're going to have two unhybridized p orbitals. So it's good to know that. That's something they can ask you as well for AP. What orbitals will be used and remaining and all that. So here's how sp looks. This is actually a little bit easier to draw. So if I have a carbon atom, sp hybridization, I'm going to put one of the sps on this side. This one I will make it a little bit fatter, I guess. And then another sp. Oh, I need to put a little bit of space there. Then another sp orbital on this side. I should have made that like a small circle. That little extra node. So in other words, this is part of that p orbital. This part and that one. Like a little exclamation point. And then this one is down that side. So that's an sp hybrid and an sp hybrid. Now you have left over two p orbitals. And now as I'm doing this, I think I'm going to, I'm sorry. I'm going to make it smaller. You don't have to erase it. You don't have to erase yours, but I'm going to make it a little bit smaller. SP. sp, and we don't really have to put that little bit. I mean, I told you you're not going to have to draw these, and if you draw them on an AP, like to help yourself, then yeah, it won't matter. There's nothing official. They're not going to ask you to do it. Just don't draw this instead of drawing a Lewis dot. If they ask for a Lewis dot, don't draw this. Draw the Lewis dot, and then you might put this there too. Okay, so here's your SP and your SP. Then one of the P's is unhybridized. I'm going to draw right here. Okay. Well, now I like to draw it a little bit longer, and those a little bit fatter, a little rounder. You can tell. Hybrid. That's your P. Maybe I would call that the PY. I mean, the way I normally draw X, Y, Z. But then look at this. Then you have another P that's going to be the PZ that kind of comes out. One goes behind the board, and then one kind of comes out of it. So that will be PZ. All right. That will be SP hybridization. Now, how will the electrons arrange? You have, remember, 4 electrons in the valence. So one goes in one of the SPs, another in the other SP. One will go into PY or PY and PZ. I'll just call it PY, PZ. You can just put P and P, but that's how they're arranged. Now, here's a really cool thing you can do. You don't have to do this, but I'm going to show you. So remember, you have your X, Y, and your Z axis, whatever. Well, I can draw easily one right next to it. This will be a much easier thing to do. That's why I had to make it smaller. And I'm gonna link it to another carbon atom. I'm just gonna draw the exact carbon atom next to it. So this is your SP of another carbon and an SP of another carbon. Okay, we'll put little circles. Then you have your P of that other carbon. The PY, and you also have the PZ. And it's important that you make them parallel, okay? You'll see where I'm going to head. Okay, so that's PY. What a mess, PY. That's PZ. Now, this carbon also has 4 electrons. One in one of the P's, another P, one in the SP hybrid, and another one in the other SP hybrid. And look, they can be used to make a bond. So we have an SP-SP sigma bond there. I better not try to label it. It could be a mess. That's an SP-SP sigma right there, overlap. These 2 orbitals overlapping. Okay? Now, what I can do is I can make a PP pi right here. So across there, I can link those. Some people just do it this way when I've seen them. My teachers were doing this in college. They were showing us this stuff. And they just do it there and there. The point is to show that there's a space in the middle where those electrons won't be. I think that it's really good that the entire P would be overlapped technically, but this part right in between will be empty, like a node, and here it will be. So these electrons are shared. They can be anywhere in the top region or anywhere in the bottom region, but they just won't be in the very center. That's a PP pi bond right there. Overlap. Okay, that's an SP-SP sigma overlap right there. And then look at this, and I'll get another color. I'll use the orange for this one. The parallel P's can make another pi bond here. And I'll take this PZ, and I'll kind of go behind that one to kind of make it look like that. So these are going to link side to side. So this P, and then down here they would also link. Oh, and I guess I could have made it a little bit smaller, but oh well. And I'll just put it here like in the front. So this P and this P overlap. So you have another PP pi. So that's a P, a PP pi, the orange. That's the same PP pi, just so you know that the yellow and the yellow, that's one pi bond, overlap, whatever. And that's because it's just the 2 orbitals coming side by side. And there's even more in the book about this, about how when orbitals overlap, remember they're like probability cloud regions. And like when they overlap, it'll show that there's some interference patterns going on. It's kind of like where one wave can interfere with another wave and cancel it out and all this stuff. They call it constructive and destructive interference. We don't have to worry about that. I don't think we have to worry about that. I can have you read that, look at it in the book, look over how the shapes look. But the main thing is, okay, so we know what kind of overlap there are. SP-SP sigma between these 2 carbons. These carbons are both sp hybridized. If I ask you to draw one of, well, I'm not going to ask you to draw one, but if you drew one, you wouldn't need to draw both of these. Now, here's the question you might see, and you might figure this out too. You're like, well, I've already gone this far. This is a triple bond between two carbons. But then they both have another single bond area, and that's where you can put a hydrogen. But I'll make the electron white. Grab no pen. And guess what that is? So, what is that chemical called? It's called ethine, or also acetylene. And actually, an interesting thing of this is you can see that will be 180 degrees. That will be straight across on this right there. But it's all going to be a linear straight across on this one. So what else do I want to tell you about that? So we could ask you what any of these bonds were. I mean, there's on the triple bond, one is a sigma, an sp sigma. Then you have a pp pi and another pp pi. Okay, maybe you can do it pi in the middle, sigma. It doesn't matter. The lines don't really mean, it doesn't matter which is which there. Okay, so I drew the sp hybridization. That was like number 2. They said to draw nitrogen. So like what I was telling you earlier, a nitrogen atom, let me slowly erase this one carbon. If I had an atom of nitrogen, the only difference is, and I'll take away the hydrogen there too, the only difference would be I would have 5 valence electrons. So there will be, so where would those 5 go? One would go in 1, 2, 3, 4, and then, hold on, what did I do there? 1, 2, where I left off, X, Y, Z, 1, 2, 3, 4, SP, SP, and then one would have to double up. Yeah, one would have to be a double up. Actually, it would have to be, okay, SP, SP, P, and P. You'd have to have, one of these would have to have like a lone pair in it. So you'd have you'd have 2 electrons here, then that would have 1, 1, and 1. And what you can do, in fact, the molecule nitrogen, it doesn't ask you to draw that, but it might, later on, if they're going to ask you about that later on, you can try and do that. You can try to answer the question, but in the molecule of nitrogen, I'll just tell you, which is like number 3 on the worksheet that you'll have to do, you would draw another nitrogen right next to it, like a mirror image, and then, of course, they would link there, there, and there, because you know that nitrogen, N2, has a triple bond. Hopefully you know that. All right, don't look on there now if you didn't know. I mean, when you do the homework later on, see if you can remember that or not. But, you pretty much have to memorize the Lewis dot diagram for Hofbrinkel, everybody in Hofbrinkel. Every one of them is a single bond except for oxygen is a double and nitrogen is a triple. Okay, so, all right, so I've shown you all those hybridizations. I guess let me move on. So, how would you do one like phosphorus with sp3d hybridization? Okay, sp3d, and this would be like in a molecule like PCl5. And like say if you drew that one, you remember me talking about the Lewis dot. I got 5 valence. This is the shortcut surrounded by a halogen or a hydrogen. 1, 2, 3, 4, 5. And so you say, okay, Cl, 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 Cl. Then of course you put in all your valence electrons. You have to show every, valence electrons. I meant to say lone pair. You have to show every lone pair electron. That would be PCl5. Now, what kind of hybridization does phosphorus have? It counts how many atoms are around phosphorus. 1, 2, 3, 4, 5. How many lone pair are on phosphorus? 0. So 5 means SPPPD. SP3D for phosphorus. Oh, I have it written up there. Why don't I do that? SPPPD. So it'll be SP3D for this one. Now, here's an interesting thing to look at too, if you care about this one. This could be asked, so I won't say that. I won't say if you care. You have to care. Okay. What kind of hybridization would chlorine have? Now, there could be, for chlorine, there could be an argument that it wouldn't hybridize. But if we were to say what kind of hybrid, if we said what kind of hybridization, I mean, if one choice were no hybridization, You could say that. But I think more general, if they're going to ask you what kind of hybridization, it's because it hybridizes. They're not going to say what kind of hybridization, and the answer is none, unless there may be a multiple choice. But what you would do is you would count. Chlorine has one atom bonded. This chlorine has one atom bonded, 3 lone pair. So 3 lone pair and 1 atom bonded is sp3. sp3 hybridization, sp-pp. Okay, you're going to see that pop up in the other ones. So anyway, to draw phosphorus, how would you draw sp3d? Well, for sp3d, sp3d2 hybridization, it becomes very easy. It becomes just like the geometry is. So sp3d is trigonal bipyramidal. Well, I don't know if it's easy to draw this, but it's easy to know what you do. So I'm going to draw my little triangle for trigonal bipyramidal. And then I'm going to put a phosphorus in the center. And here's a hybrid. Here's a hybrid. Here's a hybrid. And then you have, let's see, one above it and one below it. So it almost looks like the one I showed you earlier, sp2 hybridization. But the difference here is these are all hybrids. That's an sp3d, an sp3d, 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 sp3d. They're all sp3d orbitals right here. Because remember, an s, p, 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 d, 5 things, you're going to get out 5 hybrid orbitals. If that's your hybrid, well, I mean, each hybrid I could put a little thing there as well. But see, since you're not going to have to officially draw them, I won't even mess with drawing the little lobes. I mean, there is a lobe down there. You know, I just might just put a little dot there, each one, whatever. But you don't really need to worry about it. But where are the electrons for sp3d hybridization? Phosphorus has 5 valence, so 1, 2, 3, 4, 5. 1 in each of those. And so then your chlorine, for example, could come along, or hydrogen, if I want to put whatever, and it could overlap right here. So if I won't really, I don't know that I'll mess around with that too much. I'll just say it because it would be. But like if a chlorine were here, and let's say the chlorine has, remember it has 3 lone pair, and then it will bond on the other side to phosphorus. So that means 1, 2, 3, 4. 1 atom, 3 lone pairs, sp3 hybridization. So it would be sp3. So it would be kind of like having a tripod right here. Like an sp3, I can kind of go sideways and say, here's my chlorine, and then I'll have a tripod like there, there, and there. Like a little tripod, 1, 2, 3. And these are all sp3, sp3, sp3. These have lone pairs in them, sp3, sp3, sp3. But this sp3 would have an electron, and it would bond with that electron of phosphorus. They would overlap. So you would have an sp3d to sp3 overlap. Would that be a sigma or a pi? It can only be a sigma. The pi, you only have a pi bond when you have 2 parallel p orbitals, okay? And you'll hear more about pi bonds later on. Later on, we talk about metals and conductivity in another chapter, not in this chapter. Okay, so anyway, I could put, if I wanted to have 5 chlorine, like a tripod, or 5 around it, I could do that as well. I believe that's the best way that they would claim that one would hybridize. The chlorine would have sp3 hybridization. Okay, and then, so the last one is sp3d2, and I've done all of them so far. I might as well do this one too. So sp3d2, that's when you have S, P, 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 D, D. 6 things around it. Can you remember what 6 things is? Octahedral. So it will be any atom that will be octahedral. Like sulfur, for example, could do this. Sulfur has 6 valence electrons, and it could hybridize them that way. And because sulfur is here in period number 3, anyone in period 3 can have d orbitals in their hybridization. But now oxygen, which is in period 2, and it has 6 valence electrons, just like sulfur. Oxygen cannot do this. We're going to show you. So, for example, you can have a molecule of sulfur hexafluoride. You've seen that. It can have 6 regions around it. So I'm going to do it like this, like X, Y, Z. But each of these is going to be sp3d2, sppdd. In SF6, it's sp3d2 hybridization. Remember? Well, 2, 2, 3, 4, 5, 6, F, 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 F. And then you put the lone pair. I won't put the lone pair here, but just to show you. 1, 2, 3, 4, 5, 6 atoms bonded, 0 lone pair, sppppdd, sp3d2 hybridization. Each of these will be an sp3d2 hybrid orbital. Now, that's kind of, the lines are there to help me see where I would draw them. So like I'd have a hybrid here, 2, 3, 4, 5, 6. Now it almost looks like this, it does, but in this case, remember, over here, that entire thing's a px orbital. But over here, this is an sp3d2 hybrid. That's also an sp3d2 hybrid. It's a different, this is a separate orbital. These are not connected. In hybridization, these are the same thing, but on the hybridization, they're not. Everything you see is an sp3d2. And because sulfur has 6 valence electrons, it's able to put 1 in each one. 1, 2, 3, 4, 5, 6. And then 6 things can come along to bond there, like 6 fluorines. So why is sulfur? Sometimes that's a question they like to ask on the AP. They'll say like OF6. Just say why from data we know that SF6 does exist, but OF6 does not exist. Okay, explain why. I mean, I don't know. That sounds a little tough. That might give you a little bit more to do. But the main reason why is because O does not have any d orbitals in its valence shell. So the O valence shell is period 2. And there are no d orbitals, so you have to follow the octet. So that's why that cannot exist. Or a better one might be which of these does exist or doesn't, explain why. But SF6, more likely they'll say that one exists, that one does not. Why does that one not exist? And then they might say, well, in that question they might have some hint. Explain about the hybridization. Address hybridization in your answer or something like that. Or they might ask you a different question. Part B. What kind of hybridization does sulfur have in this? So sulfur would have SPPP, SPPPDD, SPPPDD. Yeah, sp3d2. Okay, what kind of hybridization would the fluorine have? It'll be just like the chlorine was. Fluorine has 1 atom bonded, sulfur, and 3 lone pair, SPPP, SPPP, sp3, sp3. Okay, all right. Okay. Oh, and another question that I didn't ask here. So, what orbitals? Like you're going to ask you on this. Identify what is a hybridization. What is the type and number of hybrid orbitals? Okay. In this case, it'll be you'd have 6 sp3d2 hybrid orbitals. Next, the nitrogen. Well, no, the sulfur. Never mind. What? Tell me the type of orbitals that are remaining. All right, so that it has and remains. So it has 1, 2, 3, 4, 5, 6 sp3d orbitals. This is sulfur. 6 sp3d orbitals. It also has 3 d orbitals. Empty. They're empty, but they are orbitals there. That's what it has for that one. So when you make this little list, and I told you this in the old video about hybridization, and told you to cross out, okay, use SPPPD, okay, and DD. Well, okay, one thing good about that is it shows you what's left over. Because you'll have 6 of these, but you'll have 3 unhybridized Ds. And again, you only have Ds if the center atom, sulfur, is in period 3 or I say higher or lower, 3, 4, 5, 6, 7. Okay. All right. Is there anything else to say on this sheet? Oh, are electrons localized or delocalized? I forgot to tell you that. Oh my goodness. Okay, localized just means the electrons are shared between the 2 nuclei. So in other words, localized electrons are electrons that are in a sigma bond. So like these 2 can be shared there. That would be a sigma bond. So like just say if that was sp. How did I do it before? I guess I did sp2 or something like that. Or no, maybe sp3. It doesn't matter. But I'll just say this. I've got 2 carbons. Okay, if I have an SP, what was it? SP sigma. Anytime you have electrons in a sigma, they are localized. Just remember the word localized means in a sigma bond, they're in between two nuclei. But now if you have pi bonds, that means you have a P, and you have another P right here. And there'll be another one, but I won't draw both of them. Should have told you this back then. These electrons are called delocalized. These are delocalized electrons. Anytime you have a p pi overlap. Now, delocalized electrons, it's amazing because materials that have delocalized electrons are good at conducting electricity, and they're also, trying to think, well, I'll just say they're good at conducting electricity, and that also might tell you that material is not as strong of a material. That it's easier to like move. Well, we'll talk about that later. I'm getting to another chapter. I'll talk about that later on. But I'll just tell you this. I'll just say that here's a neat thing. That when electricity is conducted, this is negative, all this little cloud area. If I put a negative charge right here, like say you brought in some negative charge electricity right there, guess what? Those electrons are going to repel away. Well, these would repel too, but they can't really go anywhere. They would kind of go crazy jumping around. But these can actually jump to the bottom. So if there's a negative, they could actually say, hey, I'm out of here. I'm down here at the bottom. Okay? Well, guess what? Having that great negative at the bottom could affect another molecule next to it and make it jump to the bottom and to the bottom and the bottom and so forth. And so it can make like a chain reaction, like a domino effect, meaning that this material could conduct electricity. So having delocalized electrons is an important thing. When do you have delocalized? Anytime you have electrons that are in pi bonds, pp pi bonds, or yeah, even just the word pi bond. Okay, so here's what I'll tell you I'd like you to do. I mean, if you didn't hear it already, but you don't have to do the first part. I kind of did it for you. If you just draw them, you'll be good. But I could ask you questions. All the questions that are below here, it says, complete the following for each compound. I would just tell you, draw the Lewis dot diagrams for these and answer these questions. Now, if you wanted to, you can try and draw the diagrams that go along with those like I did. But if you can at least visualize them, then that's good enough. You don't really have to draw them. But isn't it weird? So AP, they can ask you any of these questions, but they're not going to say to draw that. Okay? And now there's one more page of the work, and this is not very difficult. But let me go over this part. I don't know if I'll do the exact one. There is one in your notes, and I didn't even really go by your notes in this lesson. I started, but then I kind of abandoned it. But I did, it says draw SP3, then draw SP2, then SP, SP3D, SP. I did all of these for you. I did them all, but I just did not make it a gold atom or whatever. But then look at this last part. And then there's a question here that said, describe the hybridization and or bond overlap for these two molecules. And I did that on the way through there. Like CH4 I did for you. It's an sp3s sigma. sp3s sigma, and so forth. I was showing you that on a lot of them. All right. So I tell you what, I'll do this molecule right here, and I'll answer the questions. And what you're going to do the ones on this worksheet. Okay? You need to do all this, okay? But I'm going to do this. It won't take long. So let me draw this one for you and then answer the questions. I'll answer the questions as if they were on the other sheet. If you feel good without looking at it, and if you want to try to go on, you don't have to look at this. But I have a hydrogen, an oxygen, the lone pair is there, carbon, triple bond to another carbon, a chlorine right here. Then I have a hydrogen here. Wait a minute. You can't have that. Oh, no. It's a double bond. I'm sorry. A hydrogen here and a hydrogen there. Now, what I'll do, kind of like on the worksheet, I can number these. I didn't number them on the worksheet. But left to right, we'll call them carbon number 1, 2, 3, 4, 5. So I'll just call that carbon number 1, carbon number 2. And here's an oxygen, here's a chlorine, and here's a hydrogen there and one there. if I need a number differentiate, I will. So here's one question they could ask, all right? Describe hybridization, bonding, overlap for this. Well, first of all, it says, identify the hybridization for each carbon atom in this molecule. All right, each carbon atom. What kind of hybridization do they have? Okay, so carbon number 1, carbon number 2, and so forth. This one, to get hybridization, remember, count how many atoms are bonded plus how many lone pair are on that atom, and that gives it to you. This is something where they like to put on, this is like would be an organic molecule right here, okay? And even though we didn't even talk about this one, obviously it's a type of an alcohol, and with a chlorine on it. I don't exactly know how I would even name with a double bond, ethene, ethanol, and ethanol, chloro, 1-chloro, 2 ethanol. I'll say that 1-chloro, 2 ethanol. Wow. Okay, I don't even know, but you're not going to have to know that one. Believe me. They're like I told you in the organic videos. They could probably just ask you like, just not even attachment on ethane. Like on ethene, you probably just have like ethanol, or chloroethane. 1-chloroethane or ethanol. Well, you don't need a 1. Well, you can put the 1, but you don't have to. Okay, never mind. Let me get back to that. Okay. All right, here we go. So what kind of hybridization on this carbon? This carbon is bonded to 1, 2, 3 atoms and 0 lone pair, sp2. Even though the diagram doesn't look like it, that would be sp2 hybridization. That one, 1, 2, 3, is also sp2. We can do all the atoms. This oxygen would be atom, lone pair, 1, 2, 3, 4, sp3 hybridization for the oxygen. Hydrogen won't hybridize, okay? Chlorine will be, I showed you that one before, 1, 2, 3, 4, sp3, and we pretty much did it. Now, another question they could ask you would be, identify the type of bond overlap. Oh, I should have left it up there. sp2, S, sp3, S, and that will be sp3. So what kind of bond overlap here? It will be an sp2, sp3 sigma. Okay? sp2, sp3 sigma. Any single bond is always a sigma in between the two nuclei. This one will be an sp2, sp2s sigma between the C and the H, sp2s sigma between the C and the H. How about between these two carbons? There would be two bond overlaps, a sigma and a pi. An sp2 sigma and a pp pi. You can't see the p. It's not drawn in there, but it's a pp pi on parallel overlap. Then you have this one, O to C or C to O, sp3, sp2 sigma, and then O to H would be sp3 to S sigma also. Okay, that's like part 2. And then the last part says, what are the bond angles? And they give you like 3 atoms. And they love to do this. I've seen this on like organic, like something on the worksheet, because organic molecule, and ask you, what are the bond angles? Because people love to look at this, and they like to say, like they'll draw it this way, and like, what's the bond angle from carbon number 1 to carbon number 2 to the H number 3, or we'll call it H number 4. Maybe that would be number 3 here. 1 to 2 to 3. From carbon 1, carbon 2 to H4, what would that bond angle be? Okay? And for that, I put 3 things for you. For that one, they will never put 4. But 1, 2, 3. Think about what is the, think about this. This is the center. Find the center of that bond angle. The angle you're looking at. 1, 2, 3. This is the central atom. Now, the center atom, think about what is the geometry of that central atom. All right, it has on it, it's attached to how many lone pair on this carbon? None. How many atoms are bonded? 1, 2, 3. Doesn't matter if it's a double bond. All that matters are how many atoms are bonded. So it has around it 1, 2, 3 atoms plus 0 lone pair. 3 things means trigonal planar. So that would be sp2, spp, sp2 hybridization. We got that part. It would be trigonal planar. So this has a trigonal planar geometry. So even though it's drawn this way, I mean, it would even be better to draw it like the double bond with a carbon and a Cl here and an H right there. And they might do that. They might not be likely to do that on AP because that would give it away a little bit more. Oh, that's 120, and that's the angle. So all this angle from there to there to there, that's a 120-degree angle right there. Now, even though it doesn't look like it on the Lewis dot, but we know it really is in the geometry. Okay, another bond angle might be, well, these are pretty much all going to be, that's 120, that's 120, because these are both the same. But how about from, this will be the last one, from C1 to O to H. C1 to O to H, I don't know. I was going to say 5 or whatever, just to be, like the diagram might be on a Lewis, they might give you a Lewis dot, multiple choice. But from C to O to H, what is that angle? Okay, so what you would do, C to O to H, what is the bond angle? All right, what is the center? Is O. That's your central atom in this part of the molecule. So that central atom, how many atoms are bonded? There'd be bonded to this one, 2. O has an H and a C. So this atom has 2 atoms bonded to it. How many lone pair are on that atom? 2. 2 plus 2 is 4. What hybridization is 4 things? SPPP, sp3. We talked about that a moment ago. It's sp3, and that would be tetrahedral. So that will be tetrahedral. Now, actually, tetrahedral is a geometry. The shape would be angular or bent. So tetrahedral geometry, angular or bent. What is the angle of angular with 2 lone pairs? It's going to be about 109.5. So it's going to be, you can say less than, probably a little bit less than. We say less than or equal, but it'll be less than 109.5 degrees from there to there to there. Now that there definitely doesn't like 109.5 there, but if you drew it correctly, it would be like a little. It'll be a that would be it. Okay, so this is something. Here's the deal: if you practice and you get good at this stuff, you'd be able to do this. Even this worksheet, you'd be able to do it really quick. It might like, oh, it's a lot of work. But no, you look at it and just say, oh, that angle, oh, that's 180 degrees, or that's 109.5 degrees, or that's 120 degrees. So it's really easy to, once you know it, you look at it on the picture and you ought to be able to figure that out. So I know the diagram isn't the best graphics there. I should have moved over one of those lone pairs a little bit on the chlorine, but that is a chlorine right there. Okay, I talked way too long. So this is a big deal. So as I told you, if you can do all this I've shown you in these 2 videos, you can get anything that they're going to ask you about: overlap, hybridization, bond angles, whatever. Oh, planar. Oh my goodness. I did not, hold on a minute. I should have added, you know what? I cannot believe this. They can also ask if these are planar. Okay, like what I meant by this, we could say, like, for example, all right, let me just put it this way. Let me go back to 3 bonds. I got to tell you this and go back to this again. From H number 4 to carbon to chlorine, for this to this to this, is this planar, or are these atoms planar or non-planar? Wait a minute, you have to have 4 atoms to do that, don't you? I think you do. Yeah. So I'll just do this. Look at the ones I'm gonna make in bold here. 1, 2, yeah, 3, 4. Are those 4 atoms planar or non-planar? Planar means, are they in the same plane? Okay. Well, since the geometry of this, remember, if this is the center atom with 3 atoms around it, that would be trigonal planar. That name even gives it away. What that means is this carbon, and I kind of drew this a moment ago, and I should have said that. I should have told you right then. So this portion of the molecule looks like it really is a flat triangle. This atom, this atom, this atom, and this atom are all in the same plane. I need to show you that on the Zoom or in a lesson with the little model sets, and it makes it a little bit easier. But these are all in the same plane, meaning I could set those down on the table, and all of these would be hitting the tabletop. None of them are going to be popping up. If they were popped up off the tabletop, that would be non-planar. That would be like a 3-dimensional. Like they're all planar, X, Y. If one pops up in the air, then it'll be X, Y, Z, and they're not planar. Okay, so that would be planar, these 3 atoms. And then, how about the atoms that I'm going to put in yellow? And so now I'll put, how about H, O, C, oh no, that wouldn't be a good, oh, an H. Oh no, I can't do that either. Not really. You know what? I don't have an example here of one that is not planar. What I'd have to do, let me think about that for a minute. Because see, here's the deal. These three are, this is tetrahedral. However, in the tetrahedral, you might remember, like let's say you have your O right there, and you got your H and your H. It's like water. Actually, it's just like water, isn't it? Oh no, it's not OH, it's OH and a C. I'll put the C there or whatever, and it will continue on. But then you have a lone pair here and a lone pair there. Well, the atoms, anytime you have three atoms, they're going to be in the same plane. If you just have three atoms, they have to be in the same plane because you could make an angle in any angle you want, and they'll all three be in the same plane. But now, if I add another atom in, it wouldn't be. So this one, O to C, C to O to H, because of the lone pairs, is going to be planar. These three are planar. But now, if I had an atom here instead of a lone pair, let's just put another H right there. How about that? Kind of weird. But let's just say I had O with two H's and a C. A C there, an H, H, and a C attached to that O. H, and a C, and a lone pair on it. These three atoms are non-planar. They're not planar. Because now this is part of the tripod, and it will, it'll be, as you see, as I tried to draw on the diagram, this kind of comes out of the board. These three can be on the board. Like you put those flat on the board, but the chalkboard, but that's going to come protruding out right there. Okay, and the lone pair will be behind it. So, okay, so planar, non-planar. Wow. I've really got to show you that with a model set. But we've done all this stuff, and that's the only thing I've left off this worksheet. I need to add one more bit and say is this planar or not planar. Oh, and I didn't even. Oh no, never mind. I'm sorry. I was about to say I didn't draw. Okay, never mind. I'm going crazy. I did the one on my notes. You're going to do that one on the worksheet. All right, I'll see you guys.